Now we'll see how to design a compression member, and also we'll check in stat how the result will be. So generally compression member, any force which tries to compress the member, so we call it as a compression member. So in IS 800 we have section 7 where it gives equation for to check the capacity of a compression member, which is AE into FCD, and AE is our effective sectional area, and FCD is the compressive stress. Okay, so which we have to obtain either through the table which is provided in IS 800, or we have to go with this equation which is provided here. First, we will check how we can use a chart. Okay, first we will take one section. Okay, we'll check in Staad. Okay, so I've created a member, vertical member, and I've given a tube section. Okay, I'll just take this property. Yeah, this one. So here we have effective area, and then again, so specific. If you go to support, we'll consider fixed support. When it comes to compression member, we have to see the effective length. So for that, there is a effective length. Effective length it depends on the end condition, so which is available here in the table 11, where it gives based on the end constraint that effective length what we have to consider will change. Uh, Example, for the current condition, I have considered a fixed end condition and the load being applied here, vertical load, which is in compressive nature. Okay, and then yeah, effective length, since it is like cantilever member, the effective length as per code, it is 2 times the length. So what are the length we are considering? I have to multiply by 2. Let's say this length is 5 meter, 5 meter. So effective length, so my actual effective effective length will become, so 2 times the 5, that is I have to consider 10 meter. Even though length is 5, because of the end condition nature of support, we have to consider it as 2 times the length. And similarly, we have conditions when it is both side pinned, you can consider the 1 times the L, and one we have a roller, another one is fixed, you can consider 1.2 times the L. And similarly you can have few other conditions. So yeah, here you can see how it is being done. Like pinned, so effective length will be the connecting points, so that is 1. Okay, and yeah, so yeah, this is cantilever one, so effective length will be 2 times the length, Ly. And similarly for fixed end and pinned and fixed end conditions, so you can refer code or you can use, and a few good videos are available in YouTube, so you can go through that, so you'll understand what is the importance of it. This is the effective length parameter what need to be used. Okay, so now area we got it, and FCD. So FCD, it is available in the table. So here you can see it start from table 9A. Okay, so for that you need to know what is your yield strength, what is your KL by R ratio, okay, and your buckling class. So yeah, so buckling class, first we will find what is our buckling class. So buckling class is available in table 10. Okay, so based on what kind of sections we are using, currently we are using a tube section, so we can consider this. So since I'm using a hot rolled one, so it becomes buckling class A. Okay, we'll take this snapshot. So since I'm using a tube section, which is this, so it is buckling class A. So I have to see buckling class A chart only. If it is a cold formed, so then you have to use a buckling class B. And then yeah, so I'll just keep it here. Okay, so this we got it since we're using a tube section. Okay, so another thing is now we have to calculate what is the KL by R ratio. KL by R. Okay, and here yeah, so based on the end condition. Okay, and now we'll find what is KL by R for buckling class A. So we got this buckling class A, and now we have to find what is our KL bar ratio. Okay, KL by R, so it is K will consider 2 and length is 5. Okay, and R, so for this is yeah, we can find in steel table, or for time being I'll get it from Staad output itself. So minimum of radius of gyration, that is 3.42 centimeter. So I'll just consider it an mm, 34.21. Okay, so this also I'll make it in mm, 5 meter. So mm, everything is in mm. So now I'll just calculate it in Excel. KL by R. Sorry, KL by R. Okay, so that is yeah, K is equal to 2 effective length. Length is 5000 mm. Okay, and R equals to 34.21, which gives us divided by, so yeah, so our ratio is this much. Okay, yeah, 292.5. 3122. Okay, and we'll verify this whether this section will work or not. First thing we have to do every time when we are doing our design, checking slenderness should be first thing which we have to do. So again, if we go back to table number 3, here as per the code, remember carrying a compressive load result from dead by an import load should be less than 180. So what we are getting is it is greater than 180. Okay, so now it's failing in the slenderness itself. Okay, so in this case we have to either we have to increase the cross section, or we have to see is there any possibility of load reduction. Okay, yeah, increasing the cross section will increase your radius of gyration, and turn you will have a reduced value, so we should make it less than 180. And okay, so this failing in slenderness, so we have to increase section. For calculation purpose, I'll just proceed with the same section. Okay, KL by or 192, and then we have as per formula we have PD is equal to A into FCD. A is 14.7, P equals to AE into FCD. So A is here 14.7. I'm just multiplying by 100 to convert centimeter into centimeter square into mm, and FCD, which I have to find using the chart here. So we know our buckling class A, column buckling class A, and here our slenderness is I think which is not there, 290. So next option is to try with increase this section. So I'll try with tube 150 by 5, which has area 28.4 and the radius of gyration 58.8 mm. So this is in centimeters, so I'm converting into mm. So 58.8, and which I'm getting 170.068, so which is less than 180, and this is fine. So in terms of slenderness ratio, it's satisfying. So next thing is to find out what is our we'll go with the basic equation what we have. So A into FCD, A we got, FCD is which is pending, so I'll go with buckling class A, which we found out for tube section, and we know what is here. So, okay, buckling class A, KL by ratio is 170, and yield strength is from 250. So I'll take this snapshot of it. Okay, so here I'll go here 150, again here it's 170, so just coinciding here. So I have an equation of that is 55. Okay, so 55. So here AE we got it 2840 from steel table, and FCD is 55, which we found out from table 9A. 9A. So I'm getting a value of 156.2, which is greater than 10 kilonewton. So then the section is fine. So now we will check in Staad. So these are all the design command what we applied, K2, and length 5, and 180 is our slenderness limit what we have given for it, and track to for getting a complete design report. Yeah, now we will see output. Okay, steel design. Yeah, here you can see. Yeah, first we'll go with the slenderness ratio. Slenderness ratio is 170, which is less than 180, and this is fine. Okay, so the first condition satisfied. So same thing what we got here. So it is satisfied now. And the next thing is compression. Compression. So here the design force what we applied is 10 kilonewton, and capacity of this section is 150.96. For tube, both since it is symmetric, both major and minor axis like capacity is same here. So it is 155 and 155.96. Okay, and yeah, 150. How much we got? 155.96, and in our Excel we got 156.2. So it is almost same. So here in the table, when you're finding if the value lies between two values, then you have to go with the interpolation. This is for compression member, and yeah, that is about compression member. But let's say you have an bracing member. So generally, it is hard to find a member which carries only compression member, which will have either tension and compression. Let's say we take about the bracing member. Okay, let's say we are applying the load here on this side. Okay, okay, yeah. So let's say when you're applying the load here, the member we here it will be in compression. This is a compression member. Another diagonal member. This member will be in a tension. Okay, and in bracing we don't use two different members because let's say if there's a wind load which is applied here, so next like in another load combination we have to apply it from opposite end. So then there's a reversal of forces. So the time what will happen, this member will be in compression, this will be in tension. So when you're designing a bracing, you have to design for both tension plus compression. So you have to see that the bracing member can able to take both compression and tension. So then I have to choose a section which carries both. I'd like to show again design commands what need to be applied. So in design, if you go select steel, and here is 800, and then code it will come by default. Then you have to apply your k values and length, effective length along the major and minor axis. So Ly is for minor and Lz is for major. So which is also defined in our code. If you go here. This is the axis which is defined by the code. Major axis is ZZ and minor axis YY. So you can see this here how it is. This is the I section. Okay, so it will be like this. Then, okay, this I section. So here the major axis is ZZ, which means which slices through this axis. So when bending happens, major bending is nothing but it bends along the major axis, that is along the flange sides. Okay, and minor axis is when it bends along the web, that's along YY axis. This is YY, okay, which bends along the minor axis. Okay, so yeah, this thing. So this concept is very much important when you are doing calculating effective length, which is in terms define your output. I'll make separate video for calculating effective length and how we have to input in Staad Pro as well.